Welcome back to the second lecture of digital modulation. In this lecture, we will start our discussion with binary amplitude shift keying or on-off keying (OOK), which is a special variant of binary amplitude shift keying. So, let's say we have a digital bit sequence. So first thing first, we have to convert this digital bit sequence into a physically realizable signal through line coding. Here you can see the red signal is a line coded signal. It is something like 1 0 1 1 0 1, whatever. So we need to digital modulate it by amplitude shift keying modulation scheme. Of course, our amplitude shift keying is binary type, so we will encode each bit at a time. So the amplitude shift keying process is modulation process is very simple. You have a multiplier block and you are multiplying this physically realizable signal of the digital bit sequence by a cos wave or a sine wave of a particular frequency fc. So this is basically OOK. Let me just explain this with the diagram. So basically, in the physically realizable signal of the bit sequence, you have high and low amplitudes. So it is, if it is unipolar NRZ, then it will be, let's say, 5 volt for 1 and 0 volt for 0. So when you are multiplying this with a cos wave of a particular frequency fc, then at the portions of this red signal where the amplitude is 5 volt, you will get some output of that particular frequency. The frequency is fc here because this is the input frequency. But the portions where the input signal is 0, anything you multiply with 0 will result in actually 0. So you will see null here. So basically, high amplitude when you are having a high voltage here, and a 0 amplitude when you are having 0 voltage here. So high voltage means 1 and 0 voltage means 0. So your digital signal is now converted into an analog signal. It is as simple as that. You are just multiplying your digital bit sequence, which is converted through line coding, and now you are just multiplying it with the output of the oscillator, which is a cos wave of a particular frequency, and this is our analog signal in the output. So it is OOK method. In the OOK method, you have two amplitudes, and one of the amplitudes is 0, another amplitude is, let's say, A. But for another type of BASK, we can have two different amplitude values, and both of them could be non-zero. Let's say in a particular scheme, we can have two different types of amplitude levels. Let's say the two amplitude levels can be, for 1 you can have an amplitude A, for 0 you can have an amplitude of B. So it is not shown here, but this is a brainstorming question for you. How can we achieve this one using different line coding techniques? This is a very important question for the exam. How we can achieve this type of ASK where we have different amplitudes for 1 and 0 using different line coding method or different modulator circuit. You can use both. There are two ways to achieve that. You can just explore and explain how we can achieve that using either of line coding technique, different line coding technique, or different modulator circuit. I think modulator circuit is using a different modulator circuit will be easier. I encourage you to explore this thing on your own. So basically, this is the general equation for amplitude shift keying in the left side. You can see here in the left side that the ST is the amplitude shift keying modulated signal. There are basically two different types of waves for 0 bit and for 1 bit. Two different types of waves. So both of these waves have same frequency fc because we are multiplying. In this case, we are multiplying the input signal, which is the representation of the bit sequence, with the output of the oscillator, which has a particular frequency fc. So the frequency is fixed for both the cases, but the amplitude for two different bits are not similar. For 0 you have an amplitude of A0, and for 1 you have an amplitude of A1. As I have said in the my previous explanation, that you can use A for one and B for another. Here it is denoted as A0 and A1, whatever it is. So special case is when your A0 is 0, it is called OOK. You can have non-zero A naught, then it is normal amplitude shift keying. But if your A naught is 0, then it is a particular type of OK, that is particular type of ASK, I'm sorry, that is OK, which is on-off keying. Here it is the block diagram of on-off keying. I encourage you to find out the block diagram for let's say a different type of amplitude shift keying where you have non-zero amplitude for both 0 and 1. Okay, so that is the modulation part. Now how we can demodulate the original bit sequence from this modulated signal ST? Basically there is nothing different from demodulating a BASK signal and an AM signal. We have, when we discussed about AM signal, we have already talked about how to modulate and demodulate different type of message signals. Let's say we had a, if you can remember, we had a message signal like this for AM discussion. We had a message signal like this, we amplitude modulated that, and then we we know how to demodulate a signal very well. There are various methods like envelope detection, like coherent demodulation. There are different ways. The interesting thing is BASK is nothing different. BASK is basically amplitude modulation. How do we know that? Remember the block diagram of SSB modulation technique or DSBC modulation technique. You should remember the amplitude modulation technique DSB-SC, double sideband suppressed carrier. If you can remember, in this case, for modulation purpose, our modulation scheme was very simple. It was something like this. If you can remember, this was our modulation scheme for DSB-SC. Message signal is multiplied by carrier signal, and that's all for DSB-SC modulator circuit. If you compare this circuit with this one, there is a whole lot of similarity. The message signal is here, empty. Where do we get a message? This message signal is actually the physically realizable form of the digital sequence. And then when we are multiplying this with our carrier signal, our output is a digital modulator signal. So basically these two modulation techniques are actually same thing. The only difference is in the message. For AM signal you can have any type of message, but for BASK signal your message should be something like this. It should be the line coded version of a digital sequence. So if we want to retrieve the digital sequence, at first we need to go backwards. So now we have this blue signal as the input of the demodulator, and we need a digital sequence. You have the blue signal as the input and we need a digital sequence. So our first task would be reaching here to here, this digital physically realizable signal, and then from here you can actually convert it to digital bit sequence. This should be something like this: 1 0 1 1 0. So first step would be reaching from blue signal to red signal by a demodulator circuit. It can be either envelope detection, or it can be, let's say, it can be coherent demodulation, depending on the type of amplitude modulation scheme that we use. You can remember that depending on the mu, you could use either envelope detection or you could use coherent demodulation technique. So depending on the mu, same as before, we can use either envelope detection, or you can use also coherent demodulation, or simply demodulate the signal by multiplying it with the carrier once again. It's up to you. So the first step is going from here to here, which we can do obviously with envelope detection. So you can see input based BASK signal is going through a band pass filter tuned to FC. Why is this necessary? When a BASK signal, this signal is transmitted through the channel, a lot of noise will be mixed with this signal. Those noise may be high frequency noise or maybe low frequency noise, depending on the channel. So if we just filter out our necessary portion using a band pass filter, all the noise will be suppressed. So this is an important phase. Using this band pass filter, we are actually suppressing the noise. Then we have this blue signal now, because the noise is actually removed from the input BASK signal. So we have the blue signal now. Then we can use either envelope detector, or we can also use coherent demodulation, whatever is fit for that particular signal. Then we have this signal, because this was our input message when we were modulating. This message was multiplied with the carrier. So now after envelope detection we have this message. But this is not the end. We have to get the digital sequence out. How we can do that? Let me just explain this with an example. how we can convert the digital bit sequence, digital signal into the digital bit sequence. Let me demonstrate that. Let's say our bit sequence is 1 0 1 1 0. So it is 1 0 1 1 0. So let's say our time period for each bit is TB. TB is the time period for each bit. Like you have this time period for one bit, then you have same time period for another bit. This time period is called TB, bit period, TB. So the thing we will do that, we will sample this signal. You already know about sampling. We will sample this signal, and the sampling period will be TB. That means we will take one sample from each TB time. So let's say our first sample, let me just use a different color for demonstration. Let's say our first sample is taken here, in the middle of the first bit. So after TB time, let's say this again in the middle of the second bit, this third sample will be here, fourth sample will be here, fifth sample will be here. So we are taking one sample in every TB seconds. So you can see that sample at time t equal to ITB. Here I denotes the number of samples. Let's say when the TB is, let's say TB is something and I is equal to 0. That means you will get 0 into TB equal to 0. Then that means you are taking a sample at 0 second. So you are taking a sample at, let's say this is a 0 second. So you take a sample at 0 second. Then at when I will be equal to 1, you will get a sample at 1 into TB equal to TB second. So this is the TB second. Then 2 TB second. Then 3 TB second. Then 4 TB second. So I is like the loop controlling variable. I is increasing and the number of samples is also increasing. And we are taking one sample at each time period. Okay, so now we are done with the samples. Then we have to make the decision. You can see that if you just look at the blue samples in the star mark here, there are samples obviously in two different levels. The first level is this and the level is this. Obviously, you will not get such good signal in the demodulation phase because noise will be mixed, and however how much filter we use, there will be some sort of distortion. Let's say the recovered signal will be something like this. This recovered signal is something like this. So we are taking one sample at every TB time period. So first sample is here, second sample is here, third sample is here, fourth sample is here, fifth sample is here. It is not perfectly one, but if we set a threshold here, let's say this is the threshold. Let's say this sample is 0.9. Ideally this should be 1, but now it is 0.9. It is, let's say, 0.7. It can happen due to the noise and distortions. It can happen. But if you set a threshold of 0.5, then you can decide, okay, if my sample is over 0.5, I will consider it 1. If my sample is under 0.5, I will consider it 0. Let's say this is 0.1. This is not perfectly 0, this is 0.1. So you can consider this at 0 because the value is less than the threshold. So there is a decision making device. You input the threshold. The threshold depends on the noise level of the channel. If the channel is very noisy, you have to set up, let's say, a lower threshold. But if the channel is very ideal, then setting a threshold of 0.5 is okay. So then you have to say that the symbol is 1 if the threshold is exceeded, and the symbol is 0 if the threshold is not exceeded. This is the whole block diagram of BASK signal. Now as you can see, it is demonstrated here again. So it's our bit sequence is 1 0 1 1 0. This is our carrier signal, and then this is multiplied actually in the modulator circuit. So the ST or the modulated signal is this one. This is the OK type of binary amplitude shift key. So when the input bit was 1, it has a high amplitude. When the input bit is 0, it has 0 amplitude, and so on. So as you can see here, VCT is a carrier signal. It's simply a cause wave of a particular frequency, and VDT is this signal, this input digital signal. We can actually expand it using Fourier series. We have already learned how we can expand the signal in Fourier series in our AM lecture and also in our previous courses. So you don't need to memorize any of this. This is just the representation that we can actually expand this signal into Fourier series. The fundamental frequency is omega naught. So you can see omega naught, 3 omega naught, 5 omega naught, these signals here, these frequencies here. Then ST is basically the multiplication of these two. There is no need to memorize these equations, but you get the idea that how we can achieve actually this signal. This is the amplitude spectrum. We all know that in the DSB SC method, if the spectrum of the signal is something like this, this spectrum is shifted to positive frequency, positive carrier frequency and negative carrier frequency. You already know that. So this is basically the spectrum shape of the original message, which is this red signal. Now as we are multiplying it with the carrier, now it is a modulated signal, and at the for the modulated signal spectrum, the original spectrum is shifted to omega c and minus omega c. The negative portion is not shown here, so it is the only positive portion. We have a reflection of this in the negative side as well. Only the positive portion is shown here. This is basically the amplitude spectrum of the BASK signal. It is same as AM signal. There is no difference. Only difference between AM and OK is basically the difference in the message. For AM signal, the message is in the raw form. It is another analog signal. But for the OK or the BASK, the message signal is actually the line coded version of a digital signal. That is the only difference. So the whatever advantage and disadvantage was holding for AM, it will still hold for ASK. Advantage is again this simple, very simple. But as we know, AM is susceptible to noise compared to FM and PM. So ASK is also susceptible to noise compared to AM and compared to compared to FSK and PSK. That's all for BASK. We will continue our discussion on BPSK and BFSK in the next slides. Thank you.